This is the second lecture of the Trustworthy Machine Learning. So let me start with a few announcements for the course. Thank you for submitting exercise 0. I guess all of you here have submitted your 0th exercise. I sent around an email confirming our receipt of your exercises, so please check your inbox. If you haven't got it, then let me know. Maybe there's something wrong. The recap session will take place at the end of October, 31st of October, during the tutorial session. And now the exercise 1 is ready, and the responsible tutor for the exercise is Johannes here. He'll also give a tutorial today after the lecture. Well, the content will be introducing exercise 1 questions. I realized I didn't really talk about grouping for the exercise last time, so I posted it on Discord as well. Please form groups of 3. I think by now you all know what to do with this, right? So please form the groups by yourself, or the other option is to wait until the deadline for forming the groups by yourself, and then we'll do the grouping for you at random. So either way is fine. Please just do it until the 31st of October if you wish to do it by yourself. Okay, with this, let's get started with the first part of the course, OD generalization. Let's start with the definitions and how to make evaluations here. Why do we care about it? Because if you just train your model on some training data, in normal cases, the performance goes down over time. Why is that? Because people change their way of life, right? So let's say you develop an app for kind of recognizing just the scene, right? Like Google Lens or kind of image recognition tool, right? And the kind of objects people use over time, it changes. So we used to use smartphones from 10 years ago or something, right? 15 or maybe 20 years ago. But now, if you look at like 30 years ago, you don't see any smartphones. So the kind of concepts that we see in everyday life changes. And also, it's not just about the kind of objects we use, but also the user behavior. Let's say you're looking at the user log, right? And over time, you're developing new features for this service. And of course, the type of logs that you get from the users will be different. So we have to basically adapt your model to new situations over time to make sure that its performance is kind of stable. And whenever you retrain a model, you need to basically introduce new data that are kind of relevant for the scenario that you're trying to deploy your model on. So that means you need some machine learning ops operations. So what is ML ops? ML ops is kind of a system that supports a continuous deployment and continuous development of your machine learning model. Because there's a continuous influx of data, you somehow have to kind of adapt your model to this continuous influx over time. It's not done automatically, right? Someone has to kind of collect data in some database and periodically update your model to make it work, right? So that's MLOps, and it's not cheap because you need to prepare this whole system on a cloud, and you need to prepare databases. Maybe these are rather cheap, but now when it comes to people who are operating it, as I said last time, they're very expensive. So ideally, we want to kind of get rid of these MLOps and make sure that the model is kind of fixing by itself whenever there's new distribution. So based on this, we can probably come up with one proposal for kind of the holy grail of machine learning, where machine learning should go in terms of OD generalization. Yeah, so I would go from like level 1 to level 5, where level 1 is kind of no machine learning case, the most extreme rudimentary case, and level 5 is machine learning system which does not require any human involvement, ideally. So level 1 means there's no machine learning system. So if you consider customer service center, yeah, there are people who are sitting on a desk and yeah, they're receiving calls and kind of taking care of the claims from the customers. There's a machine learning model, right? But the task is super repetitive. Um, it tends to be expensive, right? Because you need to hire people and it's not scalable. When there are 10 times more customers, then you probably need to hire 10 times more people to address them. And now people realize, yeah, this is inefficient, so they develop a machine learning system. But of course, the kind of services that they offer changes over time. So if you just train a machine learning model once, then it's not going to work a year after. So there has to be periodic training again. So let's say you have to train it every month. Then every month you need to collect a new set of data and annotate them. It's costly. And then the ML engineers will sit there and do the training and deployment. Now level 3 is, let's say you need a bit less frequent updates on the model, because now the model is kind of more robust to changes in the situation. Yeah, then instead of every month, you just need to update the model every year. And that's going to be cheaper because now you probably need less people taking care of the data, and also you need less annotations. But ideally, we want to probably go without any additional annotation of the data. That's kind of level 4. And there, you train a model once, and you probably need a few changes of the model. Like one way you can do it is probably you can train like thousands of models at once. And then as time goes by, you just choose one of these models that's kind of best for the current situation. In that case, you actually don't need to train any additional new model, but there still has to be someone who's sitting there and deciding, yeah, now given the situation, maybe this is the best model. Yeah. So maybe here some minimal number of ML engineers are needed. And finally, there's no, in level 4, there's no ML ops at all. So there's no ML expertise needed at all. You're just a plain business owner and you know what to do with this machine learning system. So that's kind of where people seem to be trying to go, right, in this machine learning domain. They try to reduce the needed amount of human intervention in the model development procedure. Yeah, so why is that? Again, I think I talked about it last time, but human cost is very expensive. So we are trying to automate stuff, right? Because we want to reduce cost, but eventually we are also introducing another type of cost, which is people who are running this automation. So, so that's kind of the goal that we have in mind for machine learning. And given that, today we wish to kind of make things more more standardized and let's introduce some concepts that we can agree upon to kind of we can build our discussion afterwards. So I like to first talk about machine learning settings. Machine learning settings is basically kind of the set of ingredients that you use for training a model and the kind of situation where the model is being deployed. Yeah, so it's very vague, very broad definition for now, but you'll see what I mean by that. So OD generalization really requires the model to have been trained on a certain type of situation, and then you want the model to be applied to new situations. So there's a bit of a difference between the situation where you train a model and where you deploy the model. So this difference has to be kind of simulated. That's where the machine learning setting comes in. So we call the situation where you train a model as development, right? Where you do a lot of things, right? Like training the model parameters and also making design choices for the model. And then you have deployment scenario where the model is actually deployed. So ML setting is kind of a statement of what is available during the development and what is given during deployment. So one example of that is yeah, basically, it's kind of an input and output of the model, right? So the input to the model is model training is kind of the set of data and this kind of expertise of the model engineers, and also kind of the expectation of the business owner, maybe who have some idea of where this model should be applied to, all this kind of soft knowledge as well. They are kind of involved in the development of the model, and then the deployment is where the model is being applied. Maybe the simplest setup here is the in-distribution generalization, supervised learning setup, which is what machine learning 101 is covering, right? You're given a single distribution, and you sample n times for training the model, and from the same distribution, you sample m times independently to set up the test distribution. And the task is to make sure that once you train a model on these n training samples, it generalizes well to m different test samples. So that's in distribution supervised learning. That's probably the simplest one. What are the development resources here? A set of annotated points from distribution P, and the deployment scenario is another set of samples from the same distribution. Okay. So we're going to take a look at more exciting OOD generalization cases later on. Yeah, so development is where training and validation is taking place. Right. I'm just making sure that I didn't miss any important content here. So yeah, I think I covered all this, right? So all soft knowledge about how to train a model and the data that's involved for training the model. These are part of the development resources, and environment is where the model is being deployed to. And now we talked about ML settings. What about ML scenarios? Machine learning scenarios. It arises a lot during the review process of machine learning papers, actually research papers. Because in many of the cases, people come up with a new setting that someone has never seen before. Yeah, they say, yeah, now I'm considering a new task here where actually differently from the previous approaches, now we assume A is available, B is available, C is available, and D is available. Yeah, it's good, right? I mean, if you have a lot of ingredients, then you can do a lot of things, which is great. But is that really relevant in real life? Can we really assume that model developers have access to all these ingredients, right? Or do they have the budget to kind of buy all these sources of knowledge? Let's say they require a huge large language model, like trillion scale large language model to do something, right? Then that means they need to have this model in-house and serve it, like potentially do some fine-tuning on it. And that could be very, very expensive. So now people then ask questions like, okay, now I get what you need for your system. Can you give an example in real life when model developers have all these resources? And then comes in the concept of real world scenario, ML scenario. To give an actual example where people have access to all these resources to train this model. Yeah. So one example that I can give for in-distribution supervised learning case, again, this is actually very, very restrictive scenario in real life. In almost no cases can you actually get the samples from the test distribution identically. Yeah. So that's what ID supervised learning means, right? The kind of training data that you get is exactly from the same distribution as the test distribution. When is that possible, right? And there are a few cases where this may be possible, which is building a system for defects in some production line, right? Like wafers. There, the condition is you have a fixed camera with a fixed point, viewpoint, and the objects are always stopping at the same location, right? So you have a guarantee that the objects will appear in the same kind of context. And then now we have exact case where we can assure the training data that's also obtained from the same production line is applicable to the same production line in the future. And there will be kind of minimal change in the distribution. That's what ID supervised learning really means. And people may criticize this for being way too restrictive, but I have this real world case where this makes sense. Yeah, so this kind of real world scenario is there to make sure that we understand, yeah, this is plausible setting. And let me talk about evaluation benchmarks a little bit as well. What is evaluation, right? You do evaluation because you want to understand what's going to happen at deployment. Yeah. Of course, you can also run some monitors during after deployment, and you can also get like customer satisfaction with the machine learning model and so on. That's another form of evaluation, but from the point of view of machine learning development, what evaluation is really doing is to simulate the actual deployment and see what is the possibility. So in the context of OD generalization, we want to understand how well our model is generalizing to unseen situations. So evaluation benchmark consists of a few factors like data set, of course. There has to be data set to simulate the model performance, right? And also there should be evaluation metric, rules for how to use the data sets, because we need the segregation of the training data and the new situation, right? So we need to kind of separate them well. So that's part of the evaluation benchmark. We also need to dictate whether the model developer has been able to kind of take a look at different resources other than just the given training data, like knowledge of what the test distribution should be like. Yeah. So that's kind of the typical way how the train val test is split. So given a development data and deployment data, so that's kind of the real world situation. And we map these into data sets. And that's how you build a evaluation benchmark. So actually the train and val belongs to the development data. And the test data is supposed to be like more like deployment scenario. Yeah, usually. And training split is used for model parameter tuning, right? Using gradient descent, for example. Doesn't have to be. And validation is used for tuning hyperparameters in general. And test is not often touched, right? You just use that for kind of measuring the final performance. And maybe you can do some method comparison afterwards on the test set. But we generally use test set more sparingly than validation. Why is the separation important? Because you can make the machine learning problem arbitrarily easier by not separating the development and deployment properly. So in the most trivial case, when the actual test samples are verbatim available during training, then it's not even a generalization problem. It's not even a machine learning problem. It's just a memorization problem. Yeah, you just need to memorize this sample, and yeah, you just need to what to do afterwards. ID generalization is slightly harder because you still need to generalize between the samples from the same distribution. It becomes harder when you have more and more gap between the training and the development and deployment. So of course, so the basic principle here is to separate them well, right? So in other words, the development data should be like 100% clean of the deployment data. Yeah. So there's a small note saying the evaluation protocol usually does not make a strict assumption on the separation of training and validation. Usually the separation of training and val is kind of up to the decision of the model developer. They can do whatever they want to do with the train and val. They can even introduce a new kind of splitting of the development data into train and val, whatever way they like. Yeah. So you'll see some example of that later on as well. Yeah, I think it's kind of repeating the same stuff, yeah, in distribution is when the splits come from the same distribution. Um, OD is when they come from different distributions. Okay, so I want to make a small side note on the separation of training and validation split because I find it super interesting. As I said, there's no clear rule in general how one should separate the training and val. But still, there are some kind of rule of thumbs that people follow when it comes to how to use train and val. The usual wisdom is the training set is used for tuning the parameters of the model using gradient descent, like gradient-based method. Yeah. So in other words, you're kind of trying to minimize the loss with respect to theta, given some hyperparameter set h. Yeah. And yeah. And now what you do on the validation is you're now tuning the hyperparameters. Yeah. So given a candidate hyperparameter, what you do is you train a model for this hyperparameter, theta star, on the validation set. And then you do it iteratively until you find a better hyperparameter, which is allowing you to generalize well to this validation set. Well, that's what a lot of people do. Yeah, but actually, no one really tells you you should be doing that. In fact, you can do whatever you like with the training and validation. For example, yeah, one simple example is you don't need to use gradient descent for tuning your parameters on the training set. You can do non-gradient based methods like zeroth order gradient descent, or is kind of a black box optimization, of course. But what's more interesting is how you can use the validation set. So instead of just training a few discrete hyperparameters, you can also train millions of hyperparameters on the validation set with gradient descent. So to give you an idea of how this is interesting or possible at all, did you know that training data is also kind of a hyperparameter? It's a hyperparameter because and it's also a million dimensional hyperparameter because that's not part of the argument that you're training when you're training your model, right? When you train a model, you're just training the inside of the model, right? The parameters, and this is dictated by the factors that comes from the outside, which is kind of the training data. So from this point of view, if you can train millions of hyperparameters, then the next interesting question is, can you actually tune your data in a way that it's conducive to better generalization? Yeah. And then comes the question of then how can we find this optimal set of training data for better generalization? Yeah. So this is kind of a meta learning perspective as well. And the cited paper here used this for training data distillation, which is the task of compressing a given training data into smaller subset of training data, such that if you train a model on this smaller subset, you still get close to the original performance of the models trained on the full data set. Yeah. So that is possible, yeah, so that's interesting. The train val splitting itself could be up to optimization. Yeah. So you can think of ways to split training and validation samples in your given development data in such a way that if you do validation of your hyperparameter on the splitting, you're going to get the best OD generalization performance. Yeah. So one way to think of it is instead of maybe splitting train and val IID fashion, maybe we can introduce an adversary who's going to divide the train and val in a way that they are kind of distributionally separate from each other as much as possible. Yeah. And then if you do hyperparameter tuning with this kind of separation, then maybe the chosen hyperparameters here are conducive to OD generalization. So that could also be part of the optimization. Yeah, so that's another creative use of validation. And also what a lot of people do eventually is they do k-fold cross-validation. And what do you do eventually, right? You find the hyperparameters that are good for this k-fold cross-validation. And using this hyperparameter, you train on the full train plus val set. Yeah, because obviously if you have more training data, it should be better. So why do you waste these validation samples just for deciding hyperparameters? Yeah. Okay, so that was a small bracket in the lecture on the validation train split. Now I want to talk about something quite paradoxical about evaluation of OD generalization. So I talked about having the importance of having to separate the training, the development, and deployment during evaluation. But eventually, if you want to really see how your model is behaving in the OD scenario that you care about, the only way to see that is to look at the OD data. More precisely, you need to get some samples from the OD deployment scenario and then give it to the trained model and see how the model is doing, right? And for seeing how the model is doing, you probably need some human to come in and tell if the model predictions are good or bad. That's a kind of annotation as well, right? So in other words, to evaluate the actual model performance on the OD scenario, you need some samples from the OD and you need some annotation on it to make a number telling you how well this model is doing. Yeah, so the situation looks like this. You kind of peep a little bit into this hidden area and get some numbers, right? The problem is, once you observe it, can you still call this OD, right? Because why do you do evaluation at all, right? Because you want to make further actions based on it, right? If you're just going to observe it and do nothing about it, then why do you observe it at all, right? So now if you, let's say you change some hyperparameters because I think, yeah, the model is not doing well on OD, yeah, then it's kind of an optimization procedure for the hyperparameter, right? Based on the OD data, which is paradoxically turning this problem into in-distribution generalization again. Yeah, because this deployment scenario is not OD anymore in the most strict sense. So now the development data gets extended to this small fraction of the deployment. So this is paradox, right? You want to measure how well the model is doing in some unknown situation, but to know how well this model is doing there, you have to kind of know this, right? And then eventually, there's never a point in time where you can actually measure this cleanly enough. Yeah, so any kind of measurement here is an approximation of the actual performance. So we have to keep this in mind when we do evaluations in OD generalization. So let me go over a few terminologies as well, because it's not a very well-founded study. Like it's not like physics. So people come up with their own definitions of terminologies, and there's no like standardization of the terms and so on. So people talk a lot about tasks, queues, labels as well. Yeah, labels, features, attributes, factors of variations. What else? Environment, domain. They're more or less similar, actually. And also biases, spurious correlations. Yeah, this kind of stuff. But I want to kind of, for the purpose of this lecture, I want to kind of unify them nicely. And we can kind of stick to this terminology. So yeah, there's no single term, unfortunately. I'm going to introduce like 2 or 3 different terminologies here, compress them into these. So let's consider discriminative learning problem here. So let's say the generative process for data is like this. You have some task label, Y. Think of that as kind of object category. And we have variable Z, which is kind of encoding everything else, like all the other factors than the task itself. And based on that, you're generating an image, yeah, input image. And now the task is to infer y from x. Okay, that's discriminative learning. I just wanted to introduce this set. That's why I'm talking about this. And now, what is task? The task is the y label given x. Okay, it can come in different forms. When it's semantic segmentation, then the x is image and y is the pixel-wise categorization. Classification, given image, what is the label? Discrete label. Localization, given image, where is the object of interest? Detection, given image, what are all instances of every object in the image given as bounding boxes? Instance segmentation, the same problem, but you need to give precise pixel-wise delineation. Task could also refer to different, also in NLP domain, you have different tasks. Given text, snippet, you need to predict the sentiment, for example. Even within the same task of classification, depending on the set of labels that you have to predict, you may have different tasks. So for example, Pascal has 20 classes and Coco has a superset of 20 classes, 80 classes, and then we say they have different tasks. Okay, so that's what task is. Now let's talk about cues, features, attributes, and factors of variations. They all mean the same thing, in my opinion. It's just how you draw boundaries in the input space. How you draw boundaries in the input space. In other words, these are all functions on the input space. Okay. So for example, let's say your input space looks like this. You have some colored objects, colored shapes, circles, triangles, and squares. And depending on how you put labels on these, let's say you want to put labels according to the color of the object. Then your cue here is the color. Yeah, you can put like human understandable label on it, or you can do it along shape as well. That's a cue. But you can also introduce a kind of a random labeling of the whole input space. That's still a cue, but the problem is that it's not understandable to humans. Yeah? But I would like to define cue in a more broad sense, that it's a function on the input space. What about task, right? Task is also a function on the input space, right? So for example, if the task is to predict the shape of the object, then the shape function over the input space is the task. So task is an instance of a cue. Yeah. So task is something that's defined by human, whereas cue is something that is already there. Yeah, already there. So because if you just have this input space, right, you never know whether a human will like to see color more or shape more here, right? So someone has to come in and say, yeah, I want to recognize shape in this case to make that into the task. Now, what about environments and domains? People talk about that a lot in OD generalization. I would say these are kind of cues that are not critical or causal for the recognition of the instances. Yeah, so, and also for a special case where a model is prone to rely on such non-causal cues, maybe these are kind of spurious correlations, then I like to call them biases. Okay, so let me give some examples. Here's a clock, right? The task is to tell which category this object is, and it's a clock, like a table clock. But now there can be a lot of other factors that are playing a role here, like it's what type of photo is this? is kind of a photo that you're going to see on Amazon for products, right? So we say it's a product photo. It's front facing. It has features like it has alarm. It's made of wood. Um, there's white background in the for this image. These are all kind of auxiliary factors that are not like part of the task, but still there. So that's task, and we can say the other factors are domains. People say style as well, but style may also be a task, so I don't use style in this case as a terminology. Okay, so that was it for the terminologies. Maybe let me go over the OD generalization settings. They can also be quite interesting. There are so many settings. That's why I wanted to get here, and that's why I had to talk about settings and all kinds of stuff so far. So ID generalization, OD generalization, domain adaptation, domain generalization, test time training, K-shot learning, continue. There's so many of them, right? But I want to introduce a kind of a unified way of seeing different variants here. So we have two stages again, development and deployment. I'm going to write down kind of available resources during development and the kind of given resources during deployment. Yeah, and so the upper bar is kind of telling you what's the distribution, what's the domain where the samples are coming from. And the lower bar shows you whether the samples are labeled or not. So in ID generalization, you always have a single domain where things are coming from. And then during development, you have annotated versions of these. And during deployment, you'll be given unlabeled samples. And then the task is to kind of generalize, put labels on them. What is the basic form of OD generalization? You'll have some distribution during development, and then you're going to have a different distribution during deployment. But during development, of course, you'll have labeled samples, and of course, at test time, you'll have unlabeled samples to solve the problem on. So that's one general formulation, but there are specific instances of this, like domain adaptation. Have you heard of domain adaptation before? No? No one? Okay, domain adaptation is, how to say, you have a shift in distribution at deployment, but you have a little bit of unlabeled samples from the test distribution available during training. Yeah, so by the way, I'm kind of intermixing the test time and deployment time, but forgive me for doing that because they're, from research perspective, very similar, but from a practical perspective, maybe you want to separate them because training and test split, these are kind of simulations of the development and deployments. But from research perspective, they're identical. Okay, so now during development, you'll have a single domain with label samples, but you can also peep a little bit into how the test distribution looks like. Yeah, but we don't have any label from there. So we can do a little bit of kind of adaptation of the maybe the first layers of the network to the kind of the new texture or new kind of styles that this new distribution will have, right? So that's kind of the idea behind domain adaptation. Yeah, in other words, you can also say you're aligning your features to the target domain before applying the same kind of. So if you have this kind of dichotomy between feature layers and the classifier layers for a neural network, what you can do is you can kind of fit your first part of the network, like feature layers, to the distribution, the statistics of the unseen domain, and then you can keep the classifier bit. And the hope is that by extracting features that are kind of helping with the current trained classifier, you're generalizing better to this new situation. That's kind of the idea. There's something called domain generalization. By the way, I don't think these names are very well named. They are kind of historical artifacts of everyone coming up with their own names, right? And then they are not very informative eventually. But this is the practice. So what is domain generalization? It means you have several domains during training, and at test time you have another domain. So during training you have n different domains, and you have at test time n plus 1th domain, which is different from any of these training domains. The key important ingredient that people assume here is that for each domain in the training set, they have the domain label. In other words, they know from which source domain these samples are coming from. So here, the kind of aim is to unlearn any how to say, impact of the domain for the feature. Yeah. So they train a model, but you try to make the model agnostic to where the sample is coming from which domain the sample is coming. Once you do that, the hope is that at test time, you're given a new domain, but you're blind to the domain information, and then the model will be less confused. That's kind of the idea. Test time training, it's also interesting. The only difference here is that the development stage continues until the deployment. So the model, normally you stop tuning the model during the development stage, of course. But now the situation is at deployment, you're given a new domain and you let the model still tune itself in this new situation automatically, right? So in a sense, you can also think of that as kind of development being extended to the deployment stage. But of course, here again, you will have unlabeled samples. It's very similar to the domain adaptation case. So people also call this source-free domain adaptation. Because now it's like a special instance of domain adaptation, but now the adaptation happens along the introduction of new data sources. So it's kind of a special case of domain adaptation. Now it's also quite similar in a sense. Continual learning is talking about something similar, especially domain incremental continual learning. So you have a single domain to train on during training, and then as the deployment stages go on, you'll be introduced to new domains sequentially. So what is the difference from the previous test time training? There are potentially two differences here. So one is that discrete domains may be introduced sequentially. That's one thing. Although even for test time training, you can also have shift in domains afterwards. So yeah, let me cancel that statement. You can have, in both cases, continuous shifts in domains. The biggest difference here is that you are labeling some of the samples here. So as new domains come in, you can select a few samples in the influx of new samples, and then use that for further development of the model. That's what continual learning is. So as you can see, there's no like clear-cut boundary between the methodologies, and when you look at papers, they also mix the terminologies quite a lot. So that's why it's important to not rely on the terminologies per se, but to make a clear representation like this figure here to make sure that people understand what is provided during development and what is given at test time. Yeah, so um, my suggestion here is not to be too much fixated on the terminologies and how we call them, but on the precise content of it, yeah, and communicating what is given and what is being tested. So let's continue the discussion of what happens if you have change in the task between the development and deployment. Okay. So again, ID generalization case, you have the same task between training and testing. Yeah. But now we are going to look at the cases where actually the task changes between training and testing. By the way, task change could also be seen as kind of a distribution shift, right? Because P of y given x is kind of changing between development and deployment. So one extreme case of that is you have some task, yeah, you have some task during training, and now at test time you're given a completely new task, and you're expecting your model to kind of solve this. This used to be kind of nonsense before LLMs, but now with LLMs this is partially possible. So we'll cover that later on as well. But normally this is impossible, right? For machine learning models with usual interface of given input, it predicts the class, for example. So you need to do some special treatment for the model using the new task samples to make it adapted to new task, right? So one simple solution to that is to introduce k different samples per class for the new task. It's called k-shot learning. So you're introducing this new task during development. When k is 1, then it's called one-shot tuning or one-shot learning. It's the most hardest case, and k can go up to as many you like, right? So this is typical case of kind of using ImageNet pre-trained models. You take a pre-trained model and then you tune your model with a few samples per class for the target task that you're interested in. There's something called meta-learning. What is meta-learning, right? It's a fancy name for something simple, I would say. So in the previous case, you just had one task for pre-training your model, but now you wish to introduce n different tasks for pre-training with the, it's like domain generalization as well, right? You have multiple domains and train a model that's kind of agnostic to domain. But here the expectation is that by introducing multiple tasks, you want the model to kind of learn to adapt to new tasks easily. So it's kind of the aim is to train the model to handle multiple tasks and kind of learn kind of meta knowledge of how to learn a task. Yeah. One specific example of that is to train an initialization that's going to work well for multiple tasks. So if you find an initialization in the parameter space that is trained only with a few steps to reach a model that is doing well for task 1 and task 2 and task 3, when you fine-tune this initialization with a few steps, right, then you found the kind of generalist model that can be adapted to new tasks easily. And then what you're going to do with task 4 is you fine-tune this generalist model with a few samples from task 4, and that's it, right? And then you're deploying this model for solving task 4. The nice thing about this meta-model approach is once you train this generalist model, then not just for task 4, right, but once you have task 5, 6, 7, right, you're going to have a few training samples from there and adapt this generalist model for each of these cases in a cheap fashion. Well, at least that's the expectation for meta-learning. Okay, and revisiting continual learning, but now there are different types of continual learning. Previously, we looked into domain incremental, but here is task incremental, where you're given new tasks over time, and you'll label some of these samples to tune the model further. Okay, so let's touch upon foundation models now, because these are quite relevant, and from setting point of view, it's quite interesting what foundation models are introducing in the machine learning domain. So if you look at LLM development, right, foundation model development, you're training the model on a huge number of domains and tasks, actually. Yeah, because LLM is also trained on a huge number of tasks, right? Because your inherently is just next token prediction task, but part of that task is to really understand, let's say, categorization of the text, because yeah, for example, the the evaluation set for text classification could be part of the training data, right? And that in itself is kind of an instance of a task that you need to solve, right? And also there are a lot of other emergent behaviors that LLMs enjoy, although it's not super clear whether the model was directly trained on such task in the pre-training set. So here, our understanding of exactly on which task and domain is it trained is not precise, but we can say that it's trained on like tons of different domains and tasks. And at deployment, the problem is not a problem, it's a good thing, right? Because the model has seen a lot of stuff. We can also, it's quite likely that any situation that the model faces during deployment will probably be part of what it has seen during training. So, now comes the question of whether OD generalization really matters for these kind of foundation models, because the models have probably seen a lot of things. Yeah, so maybe the proportion of unseen cases here is pretty small. Yeah, so that's I would say unsolved question for now, but also it's always possible to craft a new type of data for the model. So if you want, as an adversary, you can always introduce OD cases for the model. So okay, so I wanted to get to the point where in practice this is good, right? That the model is trained on a lot of stuff, and that means it probably doesn't matter whether the model, we probably don't have to worry too much about whether the model is generalizing well to OD or not, because yeah, the training set is covering a lot of them. But academically, from the point of view of technological advancement, this may pose a problem, because one of the problems that LLM evaluation benchmarks are experiencing nowadays is that the test samples for evaluating the models are reported to be included in the training of these foundation models. Yeah, and also a lot of people who are playing in this benchmark actively and illegally try to incorporate these samples in the training to get better positions in the benchmark. They have all the reasons why they want to put on the top 5 list of this benchmark, because that's directly related to the funding capabilities for their startups, for example. So with this monetary reward, it makes a lot of sense for them to kind of do this kind of stuff. And for the overall community, this is not good, right? Because we don't really understand which model is better, and also it's not a faithful representation of the true progress of the technology. So potentially in the long run, this could hinder the progress. So in a sense, including a lot of data is good, but also from the perspective of tracking progress, maybe this is posing challenges. Right, so that was a quick digression into foundation models. I also want to talk about transfer learning, which can also be drawn in terms of the diagrams that we have now. Transfer learning refers to the case where you have some task during training, and you have some okay. Yeah. So yeah, transfer learning is essentially one. It could be seen as kind of a generalization of K-shot learning, where K-shot learning sees one task first and then introduces K samples per class, right? So one way to generalize that is you assume that the model is trained on a sequence of different tasks, upstream tasks, and then later on it's trained on downstream tasks to perform well on this downstream task. Yeah. So yeah, I wouldn't. At this point, I wouldn't really differentiate between K-shot learning per se and transfer learning. Transfer learning is, I would say, more general form where it could incorporate other models than classifiers, because K-shot learning has some connotation for classifiers, right? Because you have K different samples for the task. But in general, like LLMs do not have this concept of K-shot and so on. So for more general models, I would say transfer learning. When you have different sources of data where you train a model on, and then later on you have to fine tune the model on different settings. So for computer vision, the usual way you pre-train the model on upstream task is by training a model on ImageNet. And these models are readily available on PyTorch and Team. And for natural language processing, typical way of doing this is using BERT models or GPT models. And these are typically available on Hugging Face pages. Well, this is a, oh, by the way, if there's a green mark on the upper right side, then that means examinable material. If there's no such mark, then it means it's non-examinable. So now we are kind of entering non-examinable part to quickly recap the pre-training techniques. So you probably know what pre-training on ImageNet looks like. You just train for 1,000 class prediction task, and then eventually you just throw away the 1,000 class classifier at the end of the network and just train a new classifier on top. And that's one easy way to adapt your ImageNet pre-trained model on your downstream task. You can also take a look at self-supervised objective, which does not make use of any class labels in the ImageNet. What you can do is you can turn this image into two different patches, maybe from different locations of the image, and then task the model to predict if these two views, they are called views or instances, views of the same instance, views, and instance means this input image, are from the same instance or not. So the task is a binary classification task of telling if the two views are from the same image or not, or from the same instance or not. And then you don't actually need any class label. And once you train with this kind of task, the hope is that the representation that's learned is useful for many of the downstream tasks eventually. Turns out to be the case in many cases, yeah. Quickly about BERT training. The training objective for BERT is kind of filling in the mask tokens during for the token sequence. So you know that in natural language processing, the sentence is turned into a sequence of tokens, right? So for example, Super Bowl 50, blah, blah, these are all tokenized into different vectors, basically. it's called token embeddings. And these vectors are fed, sequence of vectors are fed into a transformer module, and then through a lot of self-attention modules, you'll get another vector sequence. And the goal is, based on this output vector sequence, for each of them, you have a classifier for tokens. And this classifier will produce the expected token for the mask part of the input. So for this mask, the predicted token is on, and then American football game. So in this case, we have 4 mask tokens in the input. And this also does not require any labeling of the text data. That's why you can extend this pre-training to a huge corpus of natural language text. And that also turns out to be pretty useful in practice for downstream transfer learning. There's GPT as well. The task for GPT is the next token prediction. It's an auto-regressive model. So given a sequence of tokens, the task is to predict the next token, just a single next token. Yeah, attention is not to, and then heart is probably the next token. And then if you want to continue the sentence, then you have to apply this auto-regression again based on the current generation, and then predict the next token, and then iterate until you generate as much as you like. And this training also allows for unlabeled training, because you just need a huge corpus of text, and then you can set up the task of next token prediction without any labeling effort. So that's how pre-training is done in general. And now the question is, what can we do for downstream task? So as I said before, you can do casual learning, of course, but I want to focus here more on what can you do with the parameters. So depending on which part of the model you are training, you can call it fine-tuning, partial tuning. You can also call this, there's also a variant called linear probing, and then no tuning as well. So I'm going to go over what each of these means. So let's say there's an input and there are many layers in between until you have an output, and I'm indicating the trainable parameters as this orange block. What fine-tuning means is you're tuning everything in between, well, basically every parameter in the model for this new downstream task. You can also do tuning of only the last layer, yeah? Because let's say your task changed, right? Then you need to put an output interface for this new task, right? And let's say the new task is for n different classes. Then you have the final layer, which is supporting the output of n-dimensional logics. And then this is n-dimensional classification task. Last layer tuning means that you're just tuning this final layer. Because last layer often cannot be reused because of the different number of classes, for example. People also call this kind of linear probing, meaning that they're kind of probe the linear dot products all over this representation space to extract some information that they want to have, right? So in other words, you're just training a linear classifier on top. But this single layer tuning can also be applied at different locations of the network. So if you look at this paper called Surgical Fine-Tuning, they consider only tuning the first block as well, and they also consider only tuning some middle layer or only tuning the last layer. So yeah, normally people expect tuning the last layer is probably the best idea, but sometimes tuning other layers may make more sense, depending on the kind of transfer you're experiencing. When it comes to natural language, so NL, large language models training, another popular approach is, well, for large language models, people also do all kinds of stuff like this, like tuning only the first layer. People do that as well. Or tuning only the last layer. People do that as well. Or tuning everything. Yeah, people do that for language models as well. But what people also do for language model is something called prompt tuning. Prompt is like a small part of the input. It could be like a prefix for the sentence that you're giving to the query that you're writing to the chatbot system. It could be the suffix of it, or it could be somewhere in the middle. Anyways, this prompt is something that you can formulate, of course. And when you formulate this prompt in the right way, then you can condition the generation of the language model as a whole into some model that is helping your downstream task. So let's say you want to turn this LLM into a kind of your writing teacher. So given your writing, you want this model to give you a score of how well you're doing in your write-up, right? Then what you can do is you can craft a prompt that is designed in such a way that the model is making a precise assessment of your writing. Yeah. So there are largely, I would say, two ways of doing it. So one is prompt engineering, which is more like black box optimization. There's also prompt tuning, which is more gradient-based optimization. Prompt engineering is quite simple. You just write. So typically when you use ChatGPT, you need to write down the instruction, right? Please grade my writing, for example. And then you may also come up with different way to say the instructions. Maybe you want to say, yeah, assume you're a good, you're a primary school English teacher. Yeah, your role is like that, and please grade my writing from that perspective. So there are a lot of freedom here, so you can come up with different prompts and see which one is giving me the best result. Or you can set up some of the training samples, like K-shot learning samples, where you have pairs of writing and the right grading that should be put on the writing. And then based on these samples, you're generating you compute the loss and then compute the backpropagation of the gradients through the whole LLM, and then apply this gradient descent on the prompt itself, where the prompt is kind of a soft prompt that lives in the continuous space. And if you do that multiple iterations on the given K-shot data, then whenever you attach this prompt on the input, your model will give you a good, reasonable grading for your writing. With language models, one could also go without any tuning at all, right? Because as I said, zero-shot learning is in principle possible with language models. You can kind of come up with a new task and say, please solve this task for me. Oh, actually, even before going there, actually, even for usual neural networks, it's possible to just go without any tuning by using non-parametric methodologies. So let's say you have a pre-trained ImageNet model. What you can do is, instead of kind of passing the input all the way through the final layer, just take the penultimate layer, like the second to last layer features, or it could be anywhere in the middle. You get some features basically. And then at test time, what you're going to do is you're going to pass an input through all these feature extraction layers and then get the feature and compare that against the features for the training samples. Yeah. And then you're going to see which training sample is this close to. And then you take a look at the training samples and take a look at the labels corresponding to these training samples. that are close to this test sample. And based on that, you can decide, yeah, because all these neighboring training samples are from class 3, I'm going to predict class 3 for this test sample. Yeah, if you do this, then you're actually not utilizing any tuning of the parameters here. So that's another possibility. You can do adaptation of your model to, well, there's no adaptation at all. You just apply this methodology on a new task, and it's new tuning for downstream task in a sense. In the context of LLM again, what people have explored as well is in-context learning. Yeah, so let's say you have the task of grading your writing again. Instead of giving that as input-output pairs for tuning some of the layers or the prompt, you can directly insert the list of examples you're writing and grade, maybe as a markdown table, right? Markdown table, or some CSV format in plain text into the input to the language model. And so the first part of the input will be like this kind of table. Yeah, there's writing and there's grade. And then the final part of your input will be, okay, given that I have this new writing that I just wrote, and I want you to give me my grade. So in this case, all the training, like K-shot training samples are included in the input to the language model as well. It's called in-context learning, where context means the input to the language model. So yeah, that's another possibility that's nowadays possible thanks to the powerful immersion capabilities of language models. So that was it basically for the settings for OOD generalization and how you can adapt your model to new situations and so on. Yeah, by the way, if you have any questions, you can always ask. So I want to talk about an important topic of, sure. Do you usually freeze all the other weights, or you use the whole network trained with this layer? So usually there are only two choices. Well, if you freeze the network, then you're freezing it, right? I mean, maybe I didn't get your question. Right. So freezing means you're not training it. You're doing the backpropagation through all the layers always, but eventually you're not adding the gradient to the parameters. That means you're not freezing. You're not tuning the layer, and that means you're freezing the layer. But if you're not freezing, then it means you're tuning the layer and you're making updates on the weights for the layer. Okay. Does that answer your question? Okay. So let's talk about hyperparameter tuning and information leakage. Yeah, I'm talking about this because, in my previous research, I have had so much trouble with this kind of information leakage, and while reading the papers in this domain, and also not just OOD generalization, but also all the other fields. So yeah, I wish to share some caveats here. So let's talk about domain generalization. So according to the definition of domain generalization, if you write down the condition for domain generalization in this way, in this plot, in this figure, it's clear that during the deployment, you should only see domain 1, 2, 3, and not domain 4. And we kind of define in a way that if you see domain 4, then you can't really call this domain generalization anymore. That's kind of the promise that we have. That's kind of the rule of the game. So we have to treat the first development stage as kind of a closed system where it's kind of airtight. You're not allowed to include any further information from outside. But information leakage could happen in a very sneaky fashion. Um, yeah, as I mentioned before, kind of taking a look at a few samples from domain 4 is an instance of information leakage, right? Because your decisions on your design choices are later on defined based on these samples. So let's take a look at a case study on that. So this is a paper from ECCV 2020. I do not wish to kind of like I don't want to say they did it wrong, but to me this paper is kind of a typical case where things can be a little bit misleading. They claim this to be domain generalization, but eventually there's so many places in the paper where the test domain information is sneaking into the model design that you can't really call this domain generalization anymore. So let's take a look at that. Okay. So to understand what's going on in this paper, you need to briefly understand what they're trying to do. So they're trying to solve the original objective of classification, let's say. Given this loss function, they want to minimize the empirical risk minimization. They get the gradient first, right? So at iteration t, they compute the gradient for the target label y for layer z. Okay, so that's usual backpropagation. And what they do specifically here is they want to clip the gradient. So if the gradient value is greater than some value, right, then they mask it out. What are they masking it out? The z feature value. Okay. So if gradient is too big, then you're kind of blocking it from the z computation. And by blocking it out, after blocking it out, you compute the new softmax by doing the forward pass across the model again. By the way, you don't need to know the full details here. I'm just explaining for the sake of explaining what they did wrong, right? And then they get the new gradient, and based on this new gradient, they do the parameter update. So setting aside whether that makes sense or not, let's take a look at kind of the design choices they're potentially making here. So one is deciding on which layer to apply this, right? So should we just consider activations or gradients? Yeah, and the second design choice is what should be the percentage to drop, or what should be the threshold here to drop? And the third design choice is okay, so they have this hyperparameter again for kind of, they don't do this for all the batches. So with certain percentage, certain likelihood, they are choosing the batch to apply this technology. So there are already 3 hyperparameters here. And let's see how they make these choices, okay? So I'm trying to tell you how to kind of spot this kind of information leakage by just reading the paper. So if you look at table 1, they do a decision on the feature drop strategies by computing the performances with different options. So one option is baseline, where you don't do anything. And then you have random dropping strategy, and then top activation, top gradient strategies, whatever they mean. And then what they do is they compute the performances on some set. It's important to understand on which set they are computing these numbers. It turns out the set where they are computing these numbers are on the test set, and also it's called leave one out domain generalization setting. So they have AC, art, paint, cartoon, sketch, and photo domains what they do is they train the model on the first 3 domains and then test it on the 4th domain and do it for live on art fashion across the domains. So the number that you see here, for example, for art paint means you trained on cartoon, sketch, and photo and then tested on art paint, hoping that this art paint is seen as a kind of a new domain for the model. But now the problem is you have just seen the number from this art domain test set. And actually, you're making a design choice based on the average of these numbers. Yeah. And what kind of choice did they make here? They decided that top gradient is the best methodology for OD generalization in their case. Which is great, but now actually you have seen the OD data set to make this decision. So from a bigger perspective, this is not OD generalization anymore. The same is here, right? So they also decide percentage of features to drop, and the decision here is based on the test results on the OD data set. And the same here. So when we read papers in this domain, we need to kind of understand exactly what are the ingredients they use, right? And it turns out in this case, the ingredients they use is the target domain samples. Actually, if you count the number of label samples, it's huge, right? Because it's one of, it's of the same size as the training set. So you're not using just a few like 1-shot, 2-shot, 3-shot samples from the OD test set. It's the full training size validation to make this decision. So it's rather a big violation of the domain generalization principle. Okay, so, but is that the problem with this single paper? No, everyone is doing this in this domain. And also there's a practical difficulty that you still need to decide the hyperparameters. How should I decide hyperparameters then, right? And then, okay, now this paper called In Search of Lost Domain Generalization is came up, and they're exactly kind of pointing to this problem in the whole community. Yeah, and then they say, okay, this is the right way of doing things. When you try to decide your hyperparameters or design choices or decide on the checkpoint to use, this decision should be part of the learning problem. It's not part of the evaluation. It should be part of the learning problem, which means the validation technology itself should be part of the methodology itself. Yeah. So when you propose a new domain generalization method, you should not just come up with the way to tune your parameters, but also the package should also contain the hyperparameter selection mechanism. Maybe it could be based on the in-distribution data, yeah, or it could be based on some held out OD set, yeah. But even that decision is should be part of your proposal. So with this package, practitioners know what to do when they're faced with a new distribution. If the package recommends you to have access to some separate held out OD data, then the practitioners will kind of bring in this data to kind of build their model, and then eventually ship this model to even newer situations. So you see the selection of hyperparameters should be part of the package. Is that clear? No? Okay. Stop me whenever anything is not clear. So yeah, this is again evaluation paradox. And this is kind of a pattern that's repeating a lot in machine learning. I'm not going to go into too much detail here. Maybe in the last lecture I can talk a little bit about this repeating pattern. So the general pattern is in machine learning nowadays, people shift a lot away from the ID generalization to kind of specialized generalization scenarios. Like OD generalization is one example. There are also other scenarios like weakly supervised learning and unsupervised learning and so on. And all of these are kind of necessitating the model developers to have limited resources compared to deployment scenario. And whenever that is happening, there's necessary, inevitable leakage of information just by doing the benchmarking and comparing against the previous methods. Yeah, because somehow you need to report the result when you simulate the deployment. And that evaluation itself is kind of leaking information about the OD. So that continues for a while, and then people overfeed a lot to the test set, and then someone comes up and say, yeah, we are all doing it wrong, and then resets the benchmark by doing the right evaluation, sort of, and then the field is dead, and another field is then created afterwards. So that's kind of the repeating pattern that I see in machine learning. Okay, so related to that, I've been saying that LLMs allow people to do zero-shot learning. I want to challenge that as well. Maybe apparently this is, yeah, zero-shot learning with LLMs is possible, right? Because that's also what you do with ChatGPT, right? You come with a task and you formulate it in English, and you ask it to do the task for you. So for example, I received an email and I want to check if this email is a spam or not. And what I'm going to do is I'm going to write, is this following email a spam? And then copy and paste the email content. For this, you don't need any dedicated training data. So this is zero shot, right? It depends, right? So I believed so, right? But I tried to develop a small algorithm as well for classifying text. And I soon realized that, okay, I want to develop a better prompt for doing the task. So, so for example, I'm wondering if prompt 1 is better or prompt 2 is better. Should I put the spam email first and then put the instruction, or put the instruction first and then the email content? To answer this kind of question, I need to quantify it somehow, right? I can't just, it's extremely difficult for me to tell which one is better just by looking at a few, like 3-4 different cases qualitatively. I need to come up with like 100 different cases of spam and non-spam emails and see which prompt is generating better results in each case. Because usually the difference is quite small, like 1-2 percentage points. And for doing that, I soon realized that, okay, I'm actually collecting annotated training samples for the model, just to do the evaluation. And this is not zero shot anymore then, right? Because you're using annotated training samples for your task to decide which one is better. So the lesson here is, if you wish to use LLMs at scale in an industrial setup, for example, there is always a need to track the quality of your application, and that inevitably requires you to annotate a few samples. And yeah, so I've seen recent kind of surge in, I'm not sure about the actual surge in the number of jobs in prompt engineering. I'm not sure if that's a real job yet, but at least some discussion around whether that's a real job. But I'm very, very suspicious about whether that's really going to be a real job, because the thought process is like this. So at least for prompt engineering, you need to collect a few annotated data to kind of track the progress. And once you collect this data, actually the next question is whether it's better to do prompt engineering or doing fine-tuning with this data. Usually the answer is fine-tuning is much better than doing black box optimization, in my personal experience. So then I'm questioning whether prompt engineering is really a thing.